All right. Okay, so thanks everyone for coming to this AI talk. And today we are very happy to have Xiaolong from UCSD as our speaker. So if you are working in the field of computer vision, you'll be very familiar with Xiaolong's work, like non-local neural networks or other unsupervised methods developed for video understanding. So in this talk, Xiaolong will give us an um, about the research done in his group about humanoid robots. So Xiaolong, you can start whenever you're ready.
Thank you. Thank you for the kind introduction. So right, so our lab now has been doing some robotics work. There's a lot of work also still tied to deeply into vision. So today is mostly about the work we do, like human-related kind of robots. So if we think about humanoid robot, so this is what Disney kind of picture what humanoid robot looks like.
I am not a licensed crossing guard, but it is safe to cross.
So famous.
How did you find me?
Probably many years
now
ago.
You hide. I will seek.
You also see the movie.
It is important to stretch. Before physical activity, I suggest you start with a quick jog.
Let's go. So I think it's really, as I'm working on these robots, I feel like it's really important to have a cute robot, right? So fundamentally, I feel like eventually, if you want to deploy a humanoid robot in the society, the biggest obstacle is not really about the techniques. Actually, it's about if like people find it's creepy or not. So like for general people to accept humanoid robot exists, and then have a humanoid robot to basically interact with humans, and then safely and then friendly. That's actually a very important aspect. So, but looking into what we emphasizing nowadays, right? So when we try to like do humanoids, we have a lot of startups now. For example, the infamous figure startup raised $700 million. If you raise $700 million, it seems it's going to be very serious. And it's doing a lot of serious tasks and then doing very well. So this is some upper body control. And then we have also a lot of work. It has been a long time that people work on like bipedal walking, right? So, so robot running. So this is I think Zhongyu's recent work, like running in Berkeley. So, so both sides, walking and by manual manipulation, there's a lot of basically important work. And then as you're thinking about it, so. But what we really want to have is actually maybe eventually is to have a robot that work with human together. So you need to move and then also manipulate hands and then upper body and lower body needs to do things at the same time. So essentially, what does it call is basically it's basically whole body control. So I think these are basically the three topics I try to cover today. So the first one is whole body control. And then our way to do whole body control is not actually emphasizing like specifically for solving tasks. Instead, we are more focusing on how the robot can express itself. So that's why we call it expressive whole body control. So it would be something looks like this, right? So you have like human that can interact and dance with the robot. So this is in our school. So essentially, so this work, the work I try to look into, basically, is actually try to, because whenever you have a roboticist and they ask the roboticist to create a robot, the first order is like this robot needs to solve some tasks. But how about can we have robot that like be friendly and interact with human, that can express its intention and feelings? And this aspect actually has never been considered. So for this work, we basically try to look into a little bit of that that how robot can coexist with humans. So this is something we are looking into. And then there's a lot other technical parts, right? So if the robot go out to the world, you need to perceive the world, and then you also need to have touch. So specifically, I would talk about two works. Basically, one is how to build a good semantic and geometry representations for robot to do mobile manipulation. And then I'm also going to talk a little bit about hands. So hand is something that I have been working for a very, very long time, not very, very long time, maybe 4 years. It's a very interesting problem because it's essentially what distinguish humans to animals. I would think like that's the most big differences. Like whether you know how to use your hands, basically how we are different from animals. And essentially a very, very like important sensors over the hands is actually tactile sensing. So I'm going to talk a little bit about our in-hand manipulation work by just using tactile sensing by feeling the objects, and then we can use the hand to do a lot of cool stuff. Right, so basically that's something I will try to cover today. And then I will start with the whole body control. So like I mentioned before, it's called expressive whole body control because we really actually are doing something that is not useful, right? So it's not for useful for solving some task per se. It's basically just trying to move like human and then have some fun with humans. So when you are looking into this work, don't take it too serious about whether this can solving any problems, right? So you just look into it like maybe more like having some fun to like have the robot have fun with humans. So some of you might have seen this video. We post it everywhere. So this is I show you again. Right, so it's following the human motion. But I think you need to wait till the end.
Shining through the city with a little funky sound. So I'ma light it up like dynamite. Whoa, bring a friend, join the crowd.
Right. So that's what happened in the end. So essentially, so there's still a lot of work to do, but roughly go through the 20 to 30 seconds, we are able to follow the human's motion. In the end, it's drifting a little bit away, but it's fine. So it's very robust. It's still walking. It's not falling down. But we did have fall down once, and then it broke the motor, and then it takes 5 days to fix. But this one is okay. It's safe. So I think the thing we try to do in here is essentially to enable the robot to have like able to follow humans' motion and then like do things like human do. So we have the robot that we can basically hug you, and then we also have the robot that basically walks around our lab to check out if everyone is working. So this is basically the office. It's the collaborative office at UCSD. So we have 7 faculties in here, and then students are sitting in here. So checking out if there are anyone. Apparently, it's no one. So essentially, we do hope that the robot to have all this capability of waving hands and hugging people and dancing and all these motions. That's something we enable the robot to do. So then, so it is anything new, right? So essentially, if you look into a lot of work like Jason did before, so there's in graphics in any like simulation in all this community. I mean, if we play games in PS5, PS4, so you already see a lot of very nice animated robots and very cool robot motions in all this game. So why is it like never? It has never ever been just like transferred to the real world. So why is this working so well in sim, but then it's not really like working in real? So the major reason is basically like if you look into the Unity robots, so we basically spotted out the degree of freedom for each joint. The one big reason is essentially that it has much smaller degree of freedom compared to like the simulated robot. I mean, in simulation, this guy in here, I think he has like 69 degree of freedom or something. But in our case, actually, we only have 19 degree of freedom. Currently, the robot is have this limitation. And it's a good thing or bad thing at the same time, right? So if you have high degree of freedom, it's hard to control. I have a low degree of freedom, then it's basically it's very hard to do sim-to-real transfer from the left to the right. And this is just a form of like comparisons on what we like the PHCS ASE. Pretty sure some Jason's paper, basically showing that the DOF is severely and largely larger than our robot we are using. We are also training our model actually in like the Locomotion clips, not just single one. So just try to emphasize our policy is not following overfit to a single trajectory. We are actually training on many trajectories. Right. So we are basically using this mocap data and then try to do motion retargeting from human data to robot data, and then use this to do kind of imitation learning. So because we have much less degree of freedom, so we basically find if you do motion like you do motion imitation for the whole body, it doesn't really transfer well to the real because a lot of motions we just cannot really do. We cannot enforce the robot to do it because it doesn't have the degree of freedoms. And then you have to enforce the robot to do it. We do it in a very strange way, and then that strange way might work in simulation, but it doesn't transfer to the real. And there's also another thing, actually, I'll just forget to mention, if you look in this table, the ticks and cross on underneath, essentially is like for graphics paper, you have this kind of a privilege information, what we call is like, you know, what is the linear velocity, what is the key point positions, what is the robot height, and these things. These are all privilege information that is like ground truths you can think of that you can get from simulation, but these observations are not obtainable in the real world. So we don't have these privilege informations to supervise the robot. So for example, some people do this kind of like humanoid learning in the mocap system, because under a mocap system you can capture the humanoids like linear velocity and key point positions and these and things. But then in the wild, when you do it in the wild, you cannot capture all this information. So without the privileged information, with small degree of freedom, so make this kind of motion imitation and transfer the real world very difficult. And we have tried like very hard and couldn't make it work. So then it comes to basically kind of compromise. We compromise the solution. Basically, you actually try to do motion imitation for the upper body, and then you ask the lower body to basically do just following a velocity command. So you want the lower body to do robust walking by following a velocity command. You can use your joystick to control where the robot goes, how fast it goes. So it's velocity control, but it's just a single point, right? So you don't care about how the leg moves. You just, as long as it moves and then it is robust in different terrains, that is good. The upper body, we still hope it can imitate the human motion. So this is the solution that we are offering, basically. So I would say, like, although this paper is for fun, but this solution itself, I feel like it's actually quite principled, because eventually when we are applying a humanoid robot, right, to actually doing some tasks, then you don't really care about like if the humanoid is walking in a like style, right? So in a good very style, or you just like working robustly is quite enough. So you don't actually care about how the object, the robot move, but then you do care about upper body because you need to do like tasks, like fixing objects and using bimanual hand to do different tasks. So then you do need to do imitation learning for the upper body to do tasks like humans do, but then the lower body, you don't actually need to have to imitate human that well because you can just use it to move to one location to the other. That should be enough. So in principle, I feel like this is like a solution that can be applied and then also like guide us for the following upwards that we are currently doing. So basically have this separation here. So that's basically the approach. There's nothing fancy. So we are basically doing, you have the CMU mocap data set. We do motion targeting to the robot, and then you have robot motion. So again, this robot motion, they're all kinematics, right? So they're all geometry. It's not dynamics, but then you train reinforcement learning policy to follow, given any like reference motion, which is geometry, and then you train a policy that track this reference motion to follow the geometry that you provide to make it work in a physical simulation of physical world. So this is an example like in simulation, right? So if you see the green dot is basically your reference motion. So this is like fighting scene. So you reference motion is the green dot. Again, we only do this motion imitation for upper body. So there's no green dot in lower body, okay? So it's upper body doing imitation. And the red dot is basically what is actually happening. So you want the robot to track, to follow the reference motions you're given. And that's transfer the real. So basically, so hitting this guy. So there's a waving. So this is another example. So you have this robot to wave. And basically, this is what we shoot in the beach. So it's important that because we are in San Diego, that we have the only advantage we have is the beach. So it's important when we have like robot work. So every work needs to have some demos on the beach. So that is very important. So this is some examples basically showing that sim-to-real transfer, and then you can see the motions are basically imitate only upper body, and the lower body is basically try to maintain stable. And there is one thing though. I mean, some might notice that basically it is stepping a lot because essentially the current design of the hardware is still. I feel like there's some non-perfect like disadvantage. Basically, like there's only 1 degree of freedom on the feet. So if you look in your feet now, it's just imagine that if you only have 1 degree of freedom, you can only go up and down. It's very hard to maintain balance when you're standing, but you have 2 degrees of freedom, right? So you can also do left and right. Just looking my feet now as well. Then basically, you can just very easily stand still because you can move a little bit left and right in front and back. So you have 2 degrees of freedom that makes standing much easier. So then it turns out it is true that like standing is actually harder than walking, and then having a maintain balance needs more than having 1 degree freedom would be very challenging, but if you have 2, it will be much more helpful. So this will be integrated to hopefully into the next generation of the robot design. So I know that this is some problem they also have figured out. Right. So this is some plots. So essentially, there's 4 parameters. The first one is XY. So we are sampling basically the motion. So this is some parameters. For example, the first plot is the XY. So the XY velocity, And then pitch is basically a role. Basically, is like the orientation, and then root height is your height of the robot, the torso of the height, how high your torso is. Your velocity is like how fast you turn. So this is basically some parameters that we got from this a CMU mocap data set, right? So there's a distribution of this, like how fast and which direction you move. And then after learning the policy, which is the second row, basically shows that we actually have quite similar. If you sample from the policy, I get quite similar distribution. And then you try to see whether you can generalize out the distribution, right? So you basically have the third row where we sample the red part, right? So you have some squares. We try to sample the red part, and then we get the green dot as the result. So basically you can see the lower part can kind of cover the middle part. So essentially, this basically shows the policy can kind of generalize a little bit out of the velocity and role and the distribution outside the train distribution. So that is important because as we are doing the testing, right? So we're actually going beyond the 800 poses, and then we can use a lot of great work from your group as well for text to motion, right? And then we have text to motion to as a reference motion, and then throw into this policy and then try to track that motion. So these are all out of distribution motion, and then we show basically we can still track that. So this is another figure. The resolution is not very high, but essentially the left and right is different. If you look very carefully, they're different, but they are almost the same. Basically showing that in motion data set, the rollout have different, the arms is moving to different places, but then in policies also have similar distributions on how the arms moves. So we have also some comparisons with like ours plus AMP. So AMP is also one of Jason's work on. So mentioned a lot of times of Jason. So a lot of work like the AMP basically is something you try to also do motion imitation for the legs, and then in the bottom is basically ours plus AMP, and then you can, if you see really carefully, I'm not sure how large is your screen, but if you see really carefully, you see that the feet when it's walking is still a little bit more attached to the ground. So the what we call is the foot clearance, right? So is it the foot is lifting up from the floor with above the floor of some distance. So what we find is like if you do motion imitation, you enforce it, the leg is also following the motion. It's very not easy. It's like you would not have less foot clearance, and then in our case, if you just try to optimize for robust walking, you have better foot clearance, and then which means you walking more stable and better without falling down. So this is work that basically, so this is using the lead authors, so trying to trouble the robot, showing some robustness. And then we have this fighting scene outside the face bears of our ECSD. So it's a very iconic symbols of the bear in the background. So basically, it's relatively robust. So the Yandong is trying to also another living order, trying to push the robot. Is able to, and students seem to be very happy. So essentially, it has so the walking is quite robust in these new shows. So this is a video that I don't know. I find this video very strange, but it's probably it's very strange. But it's imitating some motion, and then it's basically we can high five, and then I have a very long boring video in here. So this video is footage on how we do experiments with this humanoid robot. So this is just walking. So try to walk in different places. So it's a 4 minute walking. So basically, I think I do want to discuss one. I mean, just want to say one thing about like working with bipedal robot, right? So I mean, if you are talking to a like VC or whatever, right? So if you want to open a startup for robotics company, which is everyone doing nowadays, so all my peers are all having a company, this and that. So essentially, it would be very like the questions always you get is why do you want to do legs, right? So can you actually just use wheels? Why is like legs is not practical and it's not working? Well, I mean, like if you walk in places like this, right? So if you want to climb up the hills and want to actually eventually go in the wild, like very wild, it's not like going to other person's home. It's not wild. I mean, it's like going to climb some mountains is wild. If you do things like that, a leg is kind of necessary. And then as a research problem, right? So itself is very interesting because like our aim in like doing works in university is try to make like impossible things possible. And like if it is obvious to be solved, then what is the fun? So I do feel like it's a very interesting problem. And then I think it will be solved like maybe 1 or 2 years. And then once it's solved and everyone would come back, basically say, oh, why not use legs? Why do we use wheels? So it's just like until it is solved, it's very, very not obvious. I mean, like 10 years ago when we do self-supervised learning, everyone is saying why it's impossible to do better than image-like classification pre-train. Now everyone is saying, oh, yeah, we should do self-supervised learning. I mean, the things is going to be like that. I think it will happen to the humanoid. It's similar. Right. Now, so we have some footage, right? So Xixin went to UTC, so had some fun there. We basically demo outside mostly. So the robot blends quite well into the crowd. So this is one thing. And then, and then we have this quite also popular videos on dancing. I think it's very fun if you look at this video. Yeah, I have a lot of fun working on this project. I mean, like, if you want to do a project, why not have some fun with it? And I think this is something that students enjoy playing. There's a lot of hardware engineering, thing, training, sim to real, whatever. But then eventually, if you're able to show the robot walk out to the world and then interact with people and then basically also go to the beach. So that will be just a lot of fun. A student basically told me that they actually didn't go to that many places, but then once they work with this robot, they got to travel a lot more in their life. So essentially that's this work. So I will pause basically to if you have some questions, I will happy to be to answer. So there's a comment that too much noise while walking. The noise part is something that we fix better now. I agree that the stepping is a little bit heavy. It helps a lot if you wear a shoe. So if you look into the demos, that is different from current one and the previous one. We are actually wearing a shoe, wearing shoes. So wearing shoes helps, looks better, also helps a little bit, but we also improve the training of RL to try to have this stepping. Basically, have we add some we add some constraint and reward on the gates. Basically, try to so that's some reward from walk this way. So there's basically the student who is the first author, the two first author, and then the one Xixin is doing parkour. So he used the parkour code base. The second co-author is basically co-first author is use a lot walk this way GitHub, and then basically we eventually just use this parkour code that Xixin developed, but then we are now adding some rewards from walk this way back into the to the robot to control the gates better. So that's basically what's getting improved. So there's a lot of small things like where to add noise, where to not add noise. So how to do randomization. How much we do randomize the mass and the root. So these are things that needs to be tuned more carefully. So again, I'm happy to get any questions. Yes.
Hello, Professor. Like my name is Sherry, and
Right.
I'm currently like studying computer science and economics at Duke, and I'm also working as a student associate at Duke Capital Partners, which is like a venture capital
Right.
and private equity. And
Okay.
I'm currently like focusing on identifying the investment opportunities in the general AI and
Okay.
also the robotics sectors.
Right.
So I have 5 questions. Would that be fine with you?
We can do it. If it is a technical question, we can do it now. But if it is non-technical, maybe we can do it later. That would be
Okay,
great.
okay.
Yeah. I mean, if it's more general questions, high level, I will be happy to answer later. But then if so I'll probably want to discuss more technical things right now. Yeah. Yes.
Yeah, so because I'm from computer science, but I don't have like a lot of robotics background, so I'm interested in learning about like the software
Right.
you guys have used for robot simulation. So is
Right.
Unity like commonly used or other platforms?
All right, so now is basically this is Isaac Jim. So it's from NVIDIA. Yeah, so that's the I think it's a very mainstream simulator used for local motion control in general. Yeah, you can search Isaac Jim. Yes.
Okay. And also like I have like a question about the intersection of like humanoid robotics and AR and VR, because I'm personally like kind of interested in MR and 3D modeling. So I'm curious about like, is there any like connections between the humanoid robotics and AR VR technologies? Like any points can integrate them together?
Right. Certainly. I think I will have some like work introduced later, in a few slides later. That is in some directions. Yeah. In these directions. I can go on and present that. But there is in general a lot of connections. Yes.
Okay, cool.
Okay.
And also like I have like another tech question about like, because humanoid robots kind of like gaining a significant attention, like as like you mentioned in this lecture. So I'm curious that what is your thought about like the most promising like kind of industrial or consumer applications for kind of this humanoid robotics?
I mean, I honestly, right. So I think this is more questions, not non-technical sides, probably it's more business sides. So I think it's something maybe we can discuss later. Like I said, in this work, I try to do useless things. The more useless, the better. So if you talk to me about useful things, I'm not going to, we can discuss later, but I encourage students to do useless things. So I feel like we want to do things that's 5 years, 10 years ahead. We do self-supervised learning 10 years ahead. So now it's useful. So it's something that we I think we want to push the frontiers, not the. If you want to talk about business, we can discuss later. Yeah.
Okay, so how could I like connect with you like after this kind of
Right,
session?
I think you can contact maybe with the organizers, and then we can discuss. Yeah. So organizer, maybe you can check with organizers, and then we can. Yeah, and then connect.
Thank you for your
Yes.
answers.
Yes. Thank you. Are there any students or any people that have things? Yeah.
Right, Xiaolong, so before you move to the next slides, I would like to
Right.
ask one question about this current slide. So your robot is kind of dancing in front of crowd, and you said it was trained via imitation learning. So I'm
Right.
what is the input to this robot so that it
Yeah.
can capture the
Right.
dancing motion from the crowd?
So it's essentially we input a reference motion. So it's just like you just extract a reference motion, and then you just ask the robot to follow that reference motion. We don't have the like real time thing, right? So it's just input a trajectory essentially to the robot, and then the robot just show that trajectory out. So that's basically it. But that is also just upper body, and then the lower body is basically you have a joystick to control it where to move. So lower body is velocity control about where to move, and upper body is how the two arms should follow a trajectory. So you can imagine you have an input that is a upper body trajectory, lower body is basically a joystick thing. So this is basically what you show in here. Sorry. Right, so I think this figure explains pretty well. So it's like the upper body's green part is you can see a trajectory, lower body is just one velocity control. Yeah.
Okay, thanks.
Yeah. About
Any cameras equipped with this robot? Yes, but we haven't do the camera part. It's something we are doing. So there's a LiDAR, there's a camera. So in here, there's actually a LiDAR. If you see this small round thing, it's a LiDAR, and then there's a real sense. So that's how they put the sensors there. So we are doing some new work that is using those, but now this one is a state-based control that you basically have motion and then velocity as input.
I want to ask about how is maintaining its balance. For example, like using the reference of the imitation learning, or it has like a huge set of control systems to balance. So I'm trying to ask this.
I couldn't quite hear, but I was guessing you say how training is done. We're using a lot of motion in training. Is it something that you are asking? Hello.
I'll try to type.
Maybe it's better if you type. I couldn't hear you actually. So if you type the answer to the chat, that will help. Right. At the same time, if there are any more questions, I can answer. But I think I can, in 1 minute, I will move on. I still have a few things. Right, maybe I can just move on. And then I will wait for the questions, and then I will answer once the question appear. Well, so there's also this, right? So, I mean, if you think about the task you want to have this, like, the real whole body control is like we not do yet, have not done yet. It's actually really coordinating your legs and arms together to do something. But it's kind of a little bit boring because everyone is showing this, like picking up boxes, right? Digit is picking up boxes for Amazon. Appatronic is picking up boxes for Mercedes, and then who knows what figures we're picking boxes for. So every humanoid company is picking boxes for some company. But that is a good example. It's essentially showing that you could do whole body control. Okay, the question come up. The rebalancing of the robot is done by the imitation learning, or it has a very good control system that is controlling fixed states based on the feedbacks. Right. So it's not. So everything is just one network. So it's all one RL policy. So the RL policy is controlling every low level. So basically, it's controlling all the joint. It's doing position control for all the joints, so specifying which joint should go to where. So that is the control, right? So there's no default control or anything. So it's all reinforcement learning. So it's one policy, but the reward is defined differently, right? So the reward, I'm not sure if I actually might have here. The reward is basically two parts, right? So the upper part, you have this Q reference, and P reference basically is like the key points. Like if your joint is close to your key point is specified, then you have a reward, like it's good. And then for lower body, the reward is different. It's basically following the velocity. V is the velocity, how where the robot is moving. So that is the, and then you want to move accordingly. That's the reward. So the upper bar reward is based on joints, and the lower part is based on 1 point of velocity. So that is reward. But the reward is just a supervision, just defining the loss function, right? But you only use this reward to train one single policy, and that single policy is controlling all the joints, position control for all the joints, right? So you specifically telling at this point in time, this joint should move there, that joint should move here. So that is the position control, and that's basically what the control did. So what you try to, if you want to try to make it robust, if you see like when we are doing training, the floor is not flat, right? So we do a lot of something we call randomization as we're doing training, right? So you are having all different kinds of floors, and then you not only randomize the floors, but you also randomize yourself. So randomize the mass of the different joints, randomize also actually the height of your root. I think that is also important, the randomization there. And then you add noise. So you assume that your KD and KP is not like inverse kinematics and all these things that they're not very accurate, or have some gaps when you're doing some errors when you are doing like controlling the real world. So you add a lot of noise as you are doing position control, right? So if it's moving to there, but then you on purposely add some noise, so it does not exactly move to there. So you just add a lot of these randomizations and obstacles, and to ask the RL to, just ask the reinforcement learning algorithm to tackle all these scenarios. No matter what happens, you should still work robustly. So that's essentially how it forces the robot to work under very difficult and challenging situations, is still be able to recover it and rebalance it. So that's basically the idea in general. All right, so hope that are different motions such as dancing and boxing control with different nodes? No. So that's very, very important. So this is again a single policy, and the policy input is the reference motion, right? So essentially, what do you train? You train a tracker. So your policy is not doing anything but track the command you are given, right? So so you are training on 800 motions. Basically, your policy can track all 800 motions. So your input is essentially the green dots. That's your input. And then your output is the red dots. Basically, output is basically try to track the green dots you are given. So you can ideally you can input basically any motions. Then the policy will learn to track. So that is very different from a lot of dynamic kind of work, because it's not overfitting to an exact motion or repeating exact motion. It's learning to track a reference motion. But this is also very common in graphics community actually. Yeah. So this is a good question. And essentially, what I was trying to say, I'll show an example later that's basically on the closure band as well. So just keep coming if you have questions. Keep shooting. I will be happy to answer. All right. So I think I will be able to maybe cover one more work actually. So I really like to introduce the Lex work. It's not released yet. So this is a whole body control. It's not humanoid, but then the technique we try out here can be applied to humanoid. So we buy this robot obviously much more ahead of our humanoid robots. I'm really a little bit unhappy because we buy B1 in June, and then September they have B2, and I was asking them, well, come on, you said you will not have another version of the Lex robot in 1 year, and now 3 months you have a new robot, right? So, but we have been working on this robot for a while now. It's also $50,000. It's not very cheap. So now I think a very interesting project that's to work on this robot. This task is very interesting because it's actually you try to move your leg and arm at the same time to achieve some task. So it's also vision based actually. So it's autonomous. All things are autonomous. So we have 2 cameras. One is on the gripper, one is on the head. So this is a real sense. So apparently they're better real sense now. We should try out. Especially we have actually tried out 4 or 5 cameras for this. Some one on the arm. Right now we are trying our 6 or 7. So there's a lot of things you need to do on selection of cameras. But anyways, so this project is fun. It's also following the same philosophy that you try to train a low-level policy to follow, to do the tracking. So what you are seeing here is that you are specifying, you have manual or other policy to specify the yellow point, right? So you try to train a low-level policy to follow, your end effector will follow, your gripper will follow the yellow point. So you basically control your whole body. As long as your gripper is getting to the yellow point, that is good, okay? So you can move up your arm, you can move down your arm, but then you can, at the same time, you can bend, right? So legs and arms move at the same time. No matter how it moves, there might be multiple solutions, but no matter how it moves, the goal is to do tracking, track the end effector, track the gripper. So that's what essentially the control policy is learning here. So once you have a tracker, so that is the same with humanoids, right? So if you have a low-level policy that can track things, then you only need another policy basically tell the low-level policy what to track. So essentially, now you have a low-level policy that learn to do this tracking, learn to put your gripper into the yellow location. You can move your leg or move your gripper at the same time, doesn't matter. Then you basically train another thing. What we all like to do is computer vision. So we have like some CNN, some pointnet or wherever encode what we see. So in here specifically, we're actually running SAM and tracking SAM trackers on the objects, and then we segment it, and then we segment the depth basically. So we have depth as input. So track and segment the foreground object depth basically. So that is our input. So you train a high-level policy basically input the vision, and high-level policies output a location. The location is where the yellow guy is. So so that is the output of the high-level policy, and the low-level policy basically need to follow that location. So the control. So high-level policy has little to do with control itself. It's just like you want to go there, so you can grasp the object. That's what the high-level policy say. And then a low-level policy is to do how to go there. So how to train a tracker to go there. So that is kind of following the same philosophy we do for the humanoid, but the humanoid part is all doing all low-level things. So this is the part. So we train a lot of objects and we try on in the wild. So I think I'm not sure how much time I have, but I like to show basically. So this is able to do this kind of oops, it falls in the end. But we could basically pick up multiple objects. So maybe I just show one object in here. And so this is, again, we have to go to the beach. I'm sorry, but I need to show the beach again and again. So this is, I think it's just such a beautiful scene, right? It's so peaceful. But there's some trash on the beach, but then we have the robot to pick up all the trash. So imagine that after all the people went away home and you left some trash there, and then you still have the robot to help you to pick up all the trash. So this is I'm showing consecutively trying to. So we did some editing because it's actually the whole video is 5 minutes, but I need to show it within a minute. So this is something good about training with RL is actually it learns to retry. So you can see try to cross it now, try to cross it out, it's not successful, and then just keep trying. And then we basically have this, and then just give me some patience, but we are able to I mean in the middle the robot stops, so someone fix it, but we are able to collect all the things in the end. So this guy is trying very hard. The gripper design have a little bit problem that if you are curious about what are problems, we can share later, but we are not happy with the gripper design. But this guy is working very, very hard to clean up all the things on the ground. So the RL give the functions of retry. So because in training in simulation, you also fail a lot of times, but then you need to regrasp to get the success. So essentially, RL helps you learn to do retrying as well. Right. So finally, not sure what will happen. It just takes some time, but finally, you get all the objects. Yeah, this gripper we need to change. Right. So basically that's that. So I think I actually take most of the time. So I have quickly go through two things, and then I will happy to answer more questions. So like I said, we spend a lot of money, 50K on this leg robot. So we want to have at least a few more projects with it. So I saw a lot of questions. I will answer it later. But this is more like now we have vision language model. So this is what we like. You have doing something following language instruction. So this is more like a mobile manipulation thing. So go to the table and grasp the objects, this sort of thing. So I think one thing that is very interesting about this work is that we are doing a new kind of a 3D and plus semantic representation. So I have been pushing the direction of generalizable neo-radiance field for a while. So the idea is basically, especially for tasks like this, you need to have geometry understanding of the scene and then also semantic understanding of the scene, because you ask the robot to follow the human instructions. So we basically, I will skip a lot of details what we do, but we do basically train a generalizable nerve that is basically not only do reconstruction of visual synthesis, but also render the vision language features. So you learn basically a 3D plus semantic representation. And we just use this representation to do some open vocabulary navigation and grasping. So this is some visualization PCA of the feature space. So this is a video basically showing you so this is like Roger is the guy who is pretending looking at cat pictures somehow. I don't know why he do that. But this is the guy, the black t-shirt guy, my student that is. So this robot is autonomous. So there's a first-person view. It's a PCA feature of what you see on the right is actually building the map, and the map is a semantic map. So essentially, also the color represents the PCA of the feature space. So it's like this generalizable nerve. You can basically get reconstruction by doing a feed forward, right? So you basically get the features by doing one feed forward. So you got able to get the geometry and also the feature, the vision language model features attached to the 3D space by just doing simple feed forward. Again, on the right is a top-down view, basically of your feature view. So it's growing and building the map in real time. And I think so this is another example. I'm sorry that the speed on the bottom is a little bit faster than the speed on the top, but essentially I try to show that first-person view on the left, top-down view on the right. Basically, you are building. You're building this feature field, feature nerve in real time to not only capture objects when you look close up, but also the scene representation. The good thing about capturing scene representation is basically you can also ask the robot, let's say, don't walk on the grass, right? So don't step on the lawn and pick up toy dog. So you can do some planning to do some avoidance of the scene, and then you can go to your target objects. So we use the duck a lot. We liked our duck a lot. So this is the vision part. So I want to finally talk about our touch part. So this is a work that I like a lot in terms of this is more like a co-design of hardware and also like learning. So this is basically from the vision perspective is also, I mean, hand is so important basically again. So I mean, 2 years ago, and it's actually 4 years ago, when we are trying to start working on hand things. I think that was with Ilya, when Ilya is still a fresh PhD student. In Berkeley, so we have this state-only imitation learning paper that's like 2020. So we are doing a lot of fun on hands, but at that time, hands are still just like a problem that is very hard because it's high degree of freedom. And then also people just wonder, like, why should we do hand? Why don't we do gripper? And then, but like after 5 years, 4 or 5 years now, everyone is like now is doing hands. So we have like maybe like 10 companies that is making hands. So it's crazy. So the thing about hands is just like in general, if you do it right, so you basically can provide a more robust grasping. So if you imagine it, if you're grasping a bottle kind of thing. So using a parallel gripper grasping is very unstable. If you're grasping with hand, very stable. So and cool things about hands we like to do is also in hand manipulation. So this is a work that we try to do rotating objects in hand and then without basically using vision. It's an interesting project for me because this project is explicitly saying no computer vision, zero computer vision. Can you use touch to do anything, to do everything? So there's a lot of advancement, obviously, like for Edison's lab, right? So Digit Facebook, also a glove from Edison's lab. So on this touch sensing, I think the tactile sensing community is very, very obsessed with the texture you capture. It has been very strange to me because for me, I feel like even the sense of touch or not touch can already tell you a lot of things. But apparently, like people study on gel side. So gel side is basically soft material, and then if you touch on it, it deforms. The deformation gives you some touch information. So what we're proposing is actually on the very, very, very extreme. Instead of modeling the detailed textures of the object you touch, we are doing extreme different things. Like we just do a very, very simple sensor, but all over the hand. So the sensor we use is a FSR sensor. So it's force sensing the normal force. And then each piece is very, very cheap. It's a $12 piece. So to make it even crazier, we basically make the sensor binary. So the binary basically looks like this. On the left is continuous sensing. So you press the sensor, you get continuous signal. On the right is pressing, and then you get binary signals. So why do I want to do binary? I mean, the reason, fundamental reason is not just because it's simple, because we can do sim to real. Because like, if it is binary, then in simulation, essentially it becomes just geometry, right? So it becomes whether two mesh collide to each other. That's basically what binary capturing. So if you see the visualization here, that's the PPO policy we train in simulation. Basically the green means touch, red means no touch. So it's all geometry. So if everything becomes geometry, sim to real will be very, very easy. The real problem of all this like soft sensor, like the tactile sensing we used before, simulation does not work because the soft material mechanism is just very, very complicated. How to model deformation in simulation, it's very, very hard and very, very hard to do sim-to-real transfer. But in here, you simplify the sensor. That means you simplify the sim-to-real process. And the hope is that even the sensors are very simple, but if you have a lot of them, you can still how you capture the information of the object. And you can think about it in terms of like, you can have a very simple mechanical design, but then you use learning to do in painting of the rest of the part. So what I'm essentially proposing is basically, so this is an example to transfer the real. So you can rotate objects even without vision in the dark. So basically, it's basically saying that it's fine to have very little signal because, like, for example, if you think about MAE, right? So you only have a few patch, you can recover the whole image. So it's basically the same kinds of philosophy in here. You can have very, very simple sensor signals, but you can use learning. You train on a lot of data. You exploit billions of data in simulation. You can train a lot of data, and then that data help you to in-paint the whole pictures. So you don't need to have a lot of information. You can basically try to train and with simple sensor, but can still rotate objects into real and generalize to different objects. So that is the in-painting in hardware. So this is rotating z-axis. So there's basically y-axis and different axes we're trying to rotate. But fundamentally, I like this work because so the design philosophy in here is basically saying that when you're doing mechanical design, so we have a student doing mechanical design. The fundamental mistakes people try to make is like you try to make the mechanics too well, it's too good. So you don't actually to push the to very extreme, like as perfect as needs to be. Maybe it doesn't need to be that perfect. You can just use learning to in-paint the rest of the parts. So basically now coming to next 2-3 years, I do think that in robotics is a very big thing to is basically a good co-design of hardware and learning. So as you are doing your design of hardware, you need to think about when this is applied to learning, which part is useful, which part is not useful. So you have to consider machine learning when you are doing the mechanical design. So you cannot, so that's why you cannot wait Unity to build robots and then you build your software on top. You have to, when you're designing the robot, you need to consider learning. So that's something that we try to push a lot in our lab. Now we're doing a lot of mechanical design. So that's basically this part. So whole body touch and vision. I'm a little bit over time, but I do think this is like 3 important elements that move on to make humanoid works. And then there's accumulating. 2 questions. Is there any empirical experience to select the joints for training? I mean, we don't select the joints. We control all the joints. There's no selection in the humanoids. It's just every joints are controlled using IO. So every lighting joints. Is all the training data collected from real world, or part of them coming from simulation? It's all, I mean, depends on projects. The first and the last project, they're all simulation. There's no real world data, except the motion capture is like if you search CMU mocap data set, it's very famous. I guess that's what your lab should know very well. It's motion capture data set. You do a lot more work than CMU do nowadays. So motion capture is very important. Now I'm happy to answer more questions. And just let me know. I'm a little bit over time.
So thanks very much, Xiaolong, for your very exciting and very interesting talk. So now we can our Q&A session, and we can have any questions from the audience. If you have you would like to ask any question, just open your mic, and then you can directly interact with Professor Wang. Yeah.